All right, so now that we've introduced the idea of the derivative as a function and done a few examples of evaluating those derivatives for given functions, we're going to kind of explore this idea a little bit more. So we used this notation before. If you have a function y equals f of x, we defined its derivative, or we notated its derivative using this f prime of x here. But there's other notations that are sometimes used to indicate the exact same thing. So again, y equals f of x. Sometimes we prefer to use the dependent variable y when defining our function, and y prime would mean the same thing as f prime of x. So y prime is another notation for that derivative. Another notation that we use a whole lot is called Leibniz notation, which I talk about down here. It's dy over dx, and we pronounce this dy dx. I want to be careful to point something out about this notation. We don't want to think of this as a fraction. Even though the notation makes it look like a fraction, technically it's not to be thought of that way. Later on, not even really in this course, but in later courses, you're taught that you actually can treat this like a fraction with the right concepts in mind. But for now, I'm going to say don't think of this thing as a fraction. Don't think of it as dy over dx. It's simply dy dx, and it represents the derivative of this function. We could also say df dx because the function is also labeled f. The following three notations are what we call, they use something that we call differentiation operators. So compare this to Leibniz notation, where here I had a dy dx. If I take the y out of that and just say d dx, by itself, that d dx doesn't mean anything. But when you apply it to a function, so you write it to the left of a function, it's saying take the derivative of that function, okay? So it's an operator. It operates on a function and produces a derivative. The same thing is true of this capital D notation, D here, or this where they have a capital D with a subscript of x. This notation is just helping you indicate what the independent variable is. We will not use these notations much at all in this class, but they do show up in other classes later. So it's important to at least see them here. Okay, now the Leibniz notation that I talked about, the dy dx, it's motivated by this definition that we gave for the derivative when we talked about rates of change in the previous section. Notice the comparison, delta y over delta x. Remember, this is an increment in x and an increment in y. As we take the limit as delta x goes towards 0, both of these values are shrinking down towards 0. But in a way that their quotient might come out to something that's non-zero or whatever this derivative would happen to equal. So the dy dx is indicating what's happening to this delta y and this delta x as delta x goes towards 0. Now dy by itself and dx by itself are what we call differentials, and we talk about those much later towards the end of chapter 3. So for now, we're not going to think of dy and dx as independent quantities. We just think of this entire thing as a single notation representing a derivative. Okay. Sometimes, just like in 2.7, when we're talking about the derivative, we may want to take the derivative at a specific value. So f prime of a is the notation we used back then. Leibniz notation, if we want to indicate something similar, we use this notation. Dy dx, this horizontal line here, vertical line, and then this x equals a in the subscript here indicates that we're evaluating this derivative at some number a. Sometimes you also see a square bracket instead of a vertical line. Okay, so now that we've dealt with the concept of derivatives a little bit, we're going to talk about the concept of differentiability. So first of all, let me go back up here because I skipped this. The act of taking a derivative of a function is called differentiation. So if I have some function f of x, I may say, in a problem, differentiate f of x. What that means is take its derivative, okay? So you're going to see this word a lot. Differentiation is the act of taking a derivative. Now, differentiation is, for a function to be differentiable, which is this definition here. Specifically, a function f is differentiable at some number a that means that f prime of a exists. Remember, we defined the derivative using a limit, and we've seen that limits can fail to exist sometimes. So it's possible that you may have a function and its derivative may not exist. We're going to look at an example of that. But before we do, let me finish this definition here. If a function is differentiable on an open interval a, b, or on any one of these other types of intervals, if it's differentiable at every number in that interval. Okay, so in this example, we're given a function y equals the absolute value of x, and what we want to do is show that this function is not differentiable at x equals 0. Okay, and here's a graph of y equals f of x, and here's a graph of its derivative, but I haven't shown you why it looks this way quite yet. You could easily see from the graph up here why this looks the way that it does, but I want to do this using the definition of a derivative. So before we jump into that, it's really, really important that you know how to define the absolute value function as a piecewise function. If y is equal to the absolute value of x, we could alternatively define y this way. X if x is greater than or equal to 0, negative x if x is less than 0. If you haven't seen this way of defining the absolute value function, just think through it for a second. When you take the absolute value of a number that's non-negative, the absolute value doesn't do anything to it. It leaves it alone. What's the absolute value of 3? It's 3. What's the absolute value of 0? 0. So when x is greater than or equal to 0, the absolute value function just leaves x alone. But what if x is negative? What's the absolute value of negative 5? Positive 5. Notice you took the opposite of what was inside that absolute value. That's what this minus here is doing. If x is a negative number, then we want the opposite of that negative number, which would be positive. Okay? So this is our alternative method of evaluating an absolute value function. And the reason we need to do this is because we need to look at the definition of our derivative involving that limit and evaluate that limit using a left-hand and a right-hand limit. So let's start by looking at the left-hand limit. What is the limit as h approaches 0 from the left of the absolute value of x plus h minus the absolute value of x all over h? Okay, well in this case, the absolute value, if we're approaching, oh, I'm sorry, let me back that up. We're not evaluating this at a function. We're specifically looking for when x is equal to 0. So let me fix what I just did. I'm not putting x in here. I'm putting 0 in here. Absolute value of 0 plus h minus the absolute value of 0 all over h. This is equal to just the absolute value of h over h. Limit as h approaches 0 from the negative side. Okay? Because this would be h minus 0 is still just the absolute value of h. Now, because I'm approaching 0 from the left, that means I'm using values of h that are smaller than 0, or in other words, values of h that are negative. And the absolute value function, according to how I defined it piecewise up here, takes the opposite of h. So this is equal to the limit as h approaches 0 from the negative side of negative h over h. Okay? Of course, this all cancels, and I get the limit as h approaches 0 from the negative side of negative 1. Because it's a constant, this is just equal to negative 1. Now do the same thing, but from the right. So I'm going to take the limit as h approaches 0 from the right of 0 plus h minus absolute value of 0 all over h. And once again, this is equal to the limit as h approaches 0 from the positive side of the absolute value of h over h. This time, because h is approaching 0 from the right, where we use values of h that are greater than 0, this numerator is going to remain unchanged. The absolute value is just going to give me h. So this is equal to the limit as h approaches 0 from the positive side of h over h. H over h is just equal to 1, so I get the limit as h approaches 0 from the positive side of just 1, which is equal to 1. My left and right-hand limits do not agree. So that would mean that the limit as h approaches 0 from both sides of 0 plus h minus the absolute value of 0 over h does not exist. Which means that my function, y equals the absolute value of x, is not differentiable at 0 because no derivative exists there. Now, if we just focus on the graph, we can make sense of this. So again, notice when we use values of h that were less than 0, we had slopes of -1, and when we use values of h that are greater than 0, we had slopes of +1. And that kind of makes sense because if you look over here, the absolute value function at any non-zero value of x will always have a slope of either -1, that's all of the tangent lines here will have a slope of -1 because we're looking at a straight line, or +1. All of the tangent lines on the right side will have a slope of +1. So because we're looking at the limit, if this stays, if we have all negative slopes here and all positive slopes here, what's supposed to be happening at 0? Those two directions are not approaching the same thing. So the absolute value function has this corner in it, and that's usually your indication that you're not going to have a different, your function's not going to be differentiable there. Okay, that's not the only way that a function can fail to be differentiable, but we are going to look in a little bit at how to determine differentiability just by looking at a graph like that. Okay, we have a theorem that's a really, really important theorem that we need to talk about. It says that if f is differentiable at a, then f is also continuous at a. So here what we're doing is we're finding the relationship between two really important properties of a function that we've talked about in this class, continuity and differentiability. So again, if we happen to know that a function f is differentiable at a number, then it must also be continuous at that number. So to prove that, we're going to use one of our definitions of the derivative. Okay, let's suppose that f is differentiable at a. Okay, if that's the case, then we can use this definition of the derivative. F prime of a is equal to the limit as x approaches a of f of x minus f of a over x minus a. Okay, remember we gave that as one of our definitions of the derivative. So what I'm going to do is just work with this this guy right here, and I'm going to notice that if I were to multiply this quotient here, this difference quotient, by x minus a, I would get cancellation here, giving me f of x minus f of a. So we're going to keep that in mind because that's going to show up here in just a minute. So right here, I'm going to be looking at the limit as x approaches a of f of x minus f of a, and it'll be clear as we get down here why we're looking at this specific limit. F of x minus f of a, like we said here, is equal to this expression. So I could substitute that more complicated expression in for this guy. Now I have a product of two functions, and according to limit law 4 from section 2.3, I can bring that limit into each of those functions. So the limit as x approaches a of this quotient times the limit as x approaches a of x minus a. Now this guy exists. The limit as x approaches a of this thing exists by the fact that we assumed that f was differentiable at a. That is the same thing as saying that this limit exists. So that means we could write that as f prime of a. This is a linear function, so the limit will exist no matter what a is, and we use direct substitution. A minus a is 0. So this whole thing comes out to 0, okay? Now, it's not immediately clear why we took that limit, but it's going to be used down here. Remember what the definition of continuity says. The definition of continuity at a specific number a says that the limit as x approaches a of f of x is equal to f of a. It's equal to whatever we would get by plugging a directly into our function. So now we're going to look at the limit as x approaches a of f of x and try to show that it's equal to f of a. And in order to do that, we're going to do a common trick in calculus, which is to make a simple expression more complicated by adding something and then taking it away. So I'm going to rewrite f of x as f of a plus f of x minus f of a. Notice all I've done is I've added f of a and then subtracted it away again. So if I wanted to go back a step, these two things would have canceled out and I would still have the same f of x that I started with. So that means I haven't actually changed anything. I've only changed the way that it looks. What I have now is a sum of two expressions, two functions, and so I can distribute my limit to each of those. The limit as x approaches a of f of a plus the limit as x approaches a of f of x minus f of a. Now up here, we dealt with that exact limit already. That's the reason we did this ahead of time. We showed that that second limit is equal to 0. This guy equals 0. F of a is a constant. Remember, we're assuming a is some specific number. So if you plug that specific number into your function f, the output will be some other specific number. This is a constant, and the limit as x approaches any number of a constant function is that exact constant, f of a plus 0, which equals f of a. That's what we needed to show to establish continuity. Okay? Now, it's extremely important to understand that even though this theorem is true, in general, the converse of this theorem is not true. It's true sometimes, it's not true all the time. And what is the converse? A converse is what happens if you take an if-then statement and you swap which statement gets the if and which one gets the then. So it is true to say that if f is differentiable at a, then f is continuous at a. It is not true to say that if f is continuous at a, then it's differentiable at a. In fact, the last example we did proves that. Take a look at my example here. Okay, the absolute value function. The absolute value function is continuous at 0. Notice I could draw this graph without picking up my pen, the whole thing. But we showed that it's not differentiable there. So continuity is not enough to say that a function is also differentiable. But differentiability is enough to say that a function is also continuous. That's what we're saying here. And I kind of spell that out right here too. Moving along. Okay, so I mentioned this before with our absolute value example, but what different ways can a function fail to be differentiable based on what we see in its graph? These are all examples of where a function is failing to be differentiable. Even though it's written here, it says a corner. This is more commonly referred to as a cusp, where these two parts of the curve kind of curve into each other instead of come at a straight line like our absolute value function. But the reason for this is because as you approach a, all of your tangent lines coming from the left are going to have positive slope in this example. And not only positive slope, but a positive and increasing, getting bigger in the positive direction. If I approach a from the right, I can see the slopes of all my tangent lines are negative and getting more and more negative. So as we approach from this direction and this direction, our slopes do not appear to be approaching a common value at a. They're going opposite directions. So this will not be differentiable. Here, we know that this function would not be differentiable at a because there's a discontinuity there. Remember, if, according to the theorem that we just proved, if this function was differentiable at a, that would imply that it's also continuous. But we see that that's not the case. So this guy is not differentiable simply because there's a discontinuity. This third example here, at a, we don't have a discontinuity and we don't have a corner or a cusp or anything like that. But what we do see is a vertical tangent, okay? And it's hard to see that sometimes especially if you're doing a rough, graph by hand. But there are several functions that do have these vertical tangent lines at a specific point. The reason that this function is not differentiable there is because from algebra, you know that when you're using slope formula to find the slope of a line, vertical lines have an undefined slope. That would mean f prime of a is undefined, which is just another way of saying it doesn't exist. So this function is not differentiable at a either. So looking at all these examples, in particular, this is the one I want to key in on a little bit. The condition that a function is differentiable implies something about the character of the graph at that point. Notice here we have a function that's differentiable at a. Okay, if I look at the point that corresponds to that x value of a, and if I continue zooming in on that part of the curve, the more I zoom in, the more that little window starts to look like a straight line. Even though it's not straight, it's part of a curve, the more I zoom in, the more it's going to appear as if it were a straight line. Whereas if I look at a function like this one, which we already know is not differentiable, it has that cusp or that corner, no matter how much I zoom in on that point there, I'm always going to have a corner. It's never going to suddenly straighten out. So that's a really, really important characteristic of differentiable functions. What we a way we describe that is we say that they are locally linear, meaning if you get close enough to a point at which a function is differentiable, it can be approximated by a line, specifically its tangent line. Okay? Another descriptive term that we use sometimes to describe that is smoothness. We say that this function is smooth here. So differentiability implies a kind of smoothness. All right. Let's see. I think we have enough time to finish. No, I think I'm going to finish the rest of this in a part 3.